We now find ourselves in a bit of a predicament. We've spent time talking about how the laws of physics force us to live in an eventually consistent world, that when we're dealing with distributed systems, we have no choice but to be eventually consistent. And yet, there are plenty of examples out there of distributed systems that provide strong consistency. So the question then becomes, have we created a contradiction? Are we lying about the state of the world? If we have systems that are distributed and yet are strongly consistent, how is that possible? How can we have that if we've established that the laws of physics prevent it? We're going to answer that question, but the first thing we need to do is we need to understand strong consistency. So we're going to provide a definition. So strong consistency means that an update to a piece of data needs agreement from all nodes before it becomes visible. This is a very simple definition. It's combined out of a number of different definitions. Each of the definitions that we found while building the course were slightly different. Some of them were very technical in nature. We wanted one that you could use to talk about people again, as well as software. So this provides us an opportunity to do that. Now, if we dive into this in a little more detail, what does it really mean? Again, if you think about a group of people instead of a group of hardware nodes, with a group of people, if you want to ask them a question, then in order to have strong consistency, they all have to agree on the answer to that question before they are allowed to present that answer. So you would ask that group of people, they would get together, talk about the answer, and once they have all decided that they know what the answer is, then they will present it. It's a bit like a jury, really. The jury has a job of making a decision. The first thing they need to do is they all need to get together in a room and come to an agreement about that decision before they present it. That's the idea with strong consistency. Now, going back to our original question, how do we have strong consistency if physics tells us that we can't? If in a distributed system, physics says you have to have eventual consistency, then how do we end up with strong consistency? We do it by introducing mechanisms to simulate strong consistency. Locks are an example of this. Now, the key here is that what we are doing is we are taking our distributed problem and we are reducing it to a non-distributed resource, in this case, a lock. You can see that in our little diagram here. The blue boxes represent our distributed system, and then we have a lock in our database. But that lock is not distributed. There is only one copy of that lock anywhere. Because it's not distributed, we can eliminate the distributed system problem. The distributed system problem only exists when you have multiple things that are responsible for the same piece of data. As long as only one thing is responsible for that data, as long as we only have one instance of the lock, it's not a distributed system problem anymore. So this allows us to eliminate this distributed system problem and give us strong consistency in our eventually consistent world. However, there's a cost associated with this, and that's something that we're going to spend a fair amount of time trying to understand. This is not free. When we introduce a lock like this, it introduces overhead in the form of contention. That overhead has consequences to our ability to be elastic, it has consequences to our ability to be resilient, and it has other consequences as well. And so we're going to dive into that in more detail in later parts of this course.